All right, today we are continuing with chapter 21. So we did aldol reactions on Monday. So today we're going to do a different reaction using enolates as nucleophiles. And it's very similar to nucleophilic acyl substitution, which is, the one reaction that we learned a bazillion variants of in chapter 20. We're going to basically do that again with enolates. And then it's going to be really important that we're going to reintroduce having a separate workup step, right? We have to usually add acid at the end to get to our final product. And so that becomes really important for the reaction we're going to talk about today, which is called the Claisen condensation. And just like the aldol, there are many variants of this, right? And so we're going to go through the classic, the intramolecular, the mixed. It's very similar to the aldol, just slightly different because using esters instead. And then sort of a variant on the Claisen condensation. So they are technically two different reactions, but they're very, very similar. So let's start with our first learning objective, which is the 4 Ps for the formation of beta-keto esters from the Claisen condensation, which is section 21.4. All right, I want to contrast this with the aldol reaction, which is what we talked about on Monday. So let's just remind ourselves of what the aldol is. So this is when you're using aldehydes and sometimes ketones, but it's much more favorable for aldehydes. And we had an aldehyde that could react with itself. So the aldehyde is being both the nucleophile and the electrophile. It needed to have those alpha protons, right? We're going to deprotonate here to form that enolate in the presence of a base. And we form our aldol product. We have an alcohol and we have an aldehyde, right? So this is aldol. Ald comes from the aldehyde, all comes from the alcohol. We could also call this a beta hydroxy aldehyde, right? So again, remind ourselves that the position next to the carbonyl is the alpha position, and the next one is beta. So beta hydroxy means that there's an OH at the beta position. So that could be called a beta hydroxy aldehyde. Okay, so that's what we talked about on Monday. 2 aldehydes reacting with itself, right, to form this aldol product. Okay, so we also learned that you can make enolates from esters. So if you were to do the analogous reaction with esters, this is what the Claisen condensation is. So we are going to analogously have one ester that can act as both the electrophile and the nucleophile. I'm going to draw it twice. So again, we need those enolizable protons there. But now we're going to not draw reversible arrows because we need 2 steps. So the first step, we need the base. And remember, when using a base with esters, you need to match the base to your ester. So here. So remember to match OR prime with our ester, right? So we want this OR prime to be the same as this OR prime, which is the same as this OR prime. Okay, so that's to avoid saponification. Okay, and then we have a second workup step. It's just the acid workup. And the product that we get is similar to the aldol. OR prime, R. Okay, let's label our alpha position. Let's label our beta position. So now, instead of having an aldehyde, we have an ester, because that's what we started with. And then instead of an alcohol, we have a ketone. So this is called a beta-keto ester. But it's an ester with a ketone in the beta position. Okay. But it's similar to the aldol in that we have our ester reacting with itself. Okay, so we make a beta-keto ester in this reaction. So in addition to comparing it to the aldol reaction, I also want to compare it to nucleophilic acyl substitution. All right, so this was all of chapter 20, all of those carboxylic acid derivative reactions. So if you recall from chapter 20, we had our carboxylic acid derivative. So in this case, it's going to be an ester, but generically, right, we had this carboxylic acid derivative plus a nucleophile, often in the presence of a base. And the overall reaction is to replace the X group with the nucleophile, right? And we formed this nucleophile acyl bond. So the Claisen condensation is this reaction where our nucleophile is now an enolate. Okay? So it is the same reaction. It's just we have the funky looking nucleophile, right? It's a weird looking nucleophile, but it's the same reaction. And in this case, our X is going to be that, our X minus is OR prime minus. So it's always starting from an ester, and you're using an enolate as the nucleophile. But it is the same thing. So as a reminder, what that enolate nucleophile looks like is this, right? So this is our enolate. Usually it's the sodium salt. So after we mix the base in, you form this enolate version of the ester such that your product, right, the acyl part is still the same, and we need to connect the nucleophile from this 3 position, right? 1, 2, 3 position. So that 3 position must be right here. So it's not different, right? We still made the acyl nucleophile bond. It's just a weird looking nucleophile. Okay? So hopefully this reaction is not totally out of left field. This is the bond that we made. Okay? So that's the overall reaction. So if you're just asked for the product, you can think about the Claisen like a nucleophilic acyl substitution, because that is what it is. Okay, so let's go through the mechanism step by step, because there is one caveat in the mechanism. So it starts off the same, exactly as you would expect. We need to form our nucleophile, as we always do in this chapter, because we don't start usually with enolates by themselves. So we have our ester with an alpha proton. The pKa of this guy is about 26. And we mix it with the base that matches our ester. It's going to pull off that proton to form our enolate. Okay, so we've now generated our nucleophile, right? So now that we have a nucleophile, nucleophilic acyl substitution tells us we have to do both addition and elimination. So we're ready to do our addition step. We can mix with our other equivalent of our ester, which is going to be our electrophile. So this is that weird arrow pushing, right? Enolates react as nucleophiles by pushing down the lone pair. The CC bond attacks the electrophile, break the weakest bond. So this should give us a tetrahedral intermediate, the same way it did for every single nucleophilic acyl substitution reaction we've ever learned. Maybe I'll do this in a different orientation to make our lives easier. And then our enolate should be attached by the 3 carbon, like so. Okay, we still have sodium over here as our counter ion. Okay, we are under basic conditions. So that means that we don't need to protonate our leaving group before it leaves because it's oxygen. So that guy right there is our leaving group. So we're able to do our elimination step of nucleophilic acyl substitution. So arrow pushing for that elimination step, you push down the lone pair of that oxygen, leaving group leaves. So we reformed the carbonyl, right? And now our nucleophile is attached. And we regenerated our base. Okay, we're gonna walk through that one more time. Step number 1, form our enolate, right? AKA make your nucleophile. Now that we have a nucleophile, step number 2 is addition, like nucleophilic acyl substitution addition, or you can think about it as nucleophile attacks electrophile. And then step 3 over here is elimination. Right? So you collapse the tetrahedral intermediate, leaving group leaves. Now, the tricky part about this is that this is the correct product. But we're not done with the mechanism. So I'm going to redraw this guy down here. So this is kind of the weird part about this, is we need to remember our pKa trends. So if we compare our product to our starting material, right, the pKa of our starting proton was about 26. Well, the pKa of this alpha proton right here is about 11 now. So it's more acidic now that we've done the reaction. So that means that we can't stop here, right? It has to keep going because it still has an acidic proton that's more acidic than the starting material. That's more acidic. So just based off of pKa's, we cannot stop here. We regenerated our base, so that means that we have base around, and that base has to deprotonate that alpha proton. Like so. Oops. And then I can draw my enolate. And there are 2 resonance structures, both of which are fine. So let's just draw them both. So here I pulled the electron density up into the ketone oxygen, but I could also do it over here into the ester oxygen. So, okay, both of these have our counter ion. Okay. So, because we have this really acidic proton, it's going to reform this enolate. And actually, this last step right here is the driving force for the reaction. And so this, it stops here. It actually will sit as that enolate until you do the workup step to get it to go back. Okay, so as we're going through the reaction, it forms the enolate, does our addition, does our elimination, and then does an extra deprotonation, and then it will sit here. And then that's why we need a second step, acid workup. And then we can have that enolate grab a proton. So that's kind of the weird part, because we get the same product back, right? So this is a rare case where you actually make the product as part of the mechanism, but your mechanism isn't done. You have to keep going because the driving force of the reaction doesn't happen until after that. Questions on that? That last part is kind of the tricky bit, I would say. You just got to know that looking at pKs, right? If you have a more acidic proton, it's definitely going to get deprotonated first, right? So it has to do that at the end. Okay, so because that last step is the driving force of the reaction, if you cannot do that last step, the reaction doesn't happen. Okay, so let's look at an example of that. So if you cannot deprotonate again, the reaction is not favorable. So let's look at an example like this. Okay. So in this case, I would use sodium ethoxide, right? I'm always going to check to make sure that my base matches my ester. Okay, and then the product we get, I'm going to replace my electrophile's X group with the nucleophile at the alpha position. Okay, so that would put 2 methyl groups here. So if we have 2 methyl groups here, right, that means that there are no alpha protons to deprotonate again. Therefore, we do not have a driving force for this reaction. So this does not go. It will be no reaction because it will favor the reverse direction. Okay, so that's an example of if you don't have alpha protons at the end, you don't have a driving force, therefore it's not favored to go forward, it wants to go backwards. And the way that you can tell that from your starting material, so it's okay if you need to draw it out to the product and then see that it doesn't have alpha protons, that's fine. But you can also just look at the starting material here, and if it only has 1 alpha proton, it's not going to go because you actually need 2. Okay, so if your starting material only has 1, that is what's going to tell you that you're not going to have enough to do that second deprotonation at the end of the reaction. Okay, so that's kind of the trick that you can look earlier and see if it's going to go or not. All right, let's do a try-me question, see if that's making sense. Know that these are hard to visualize. They're definitely hard to visualize. So here, predict the product of the following Claisen condensation. So I'm giving you an ester, right? Ester is reacting with itself because there's nothing else there to react with. We have a base. Does the base match the ester, and then what is the product? So I'll give you a couple minutes to think about this. Feel free to chat with your neighbors to see if they are getting the same answers. Gonna be 10 more seconds. Get your answers in. All right, let's see what we got. Nice. Okay, great. So most people got the right answer, was just B. C is a very common incorrect answer. You just didn't count your carbons, right? Which is a very, very common mistake. So let's talk through the logic behind this. That's really good though. I know how difficult these are to visualize because the enolates look so strange. Let's go here. Okay, so you were given this, and I'm going to draw it twice because we know it's going to react with itself. You were given the reagents. You were asked for the product. So the first thing that I always check is, does the base match our ester? Yes, because if it's NaOH, right, it's going to do saponification instead. So we're good there. Next, for our nucleophiles, let's say this one, do we have 2 protons? Check, which means that there is going to be a driving force for this reaction, right? Because we need to be able to do that second deprotonation, unlike up here where we only had 1 alpha proton. So we had 2 alpha protons, so that's good. So we can form an enolate, and it's going to attack from that alpha carbon. And then for our electrophile, which is the other one, right? Our electrophilic location is going to be that carbonyl, and this OET is going to be our leaving group, or our X group. So we're going to replace that OET with our nucleophile. Okay, so we're gonna replace the OET with the nucleophile attached from the alpha position. And then directly attached to the alpha position is this phenyl group. There is not an extra carbon there. So again, counting our carbons is a good idea always to make sure that we're not losing it. Questions? Now that you've had to do one yourself? They kind of look familiar to things that you've seen before, hopefully. Okay. I know that they look weird, right? Like these are weird looking nucleophiles. I get it, but it is the same. I promise you it's the same. Okay, so let's just do an example going backwards, because I do think that backwards is harder. So if you need to go to the starting material, and you are given this product like so. Okay, so when going backwards, the kind of first thing you need to determine is which bond is the one that I'm breaking or making, right? So I think in Claisens, people can normally tell that it's going to be in between the two carbonyls, right? That we're going to be making or breaking this bond. So we kind of have two options, right? So we've got this one and we've got this one. I see fingers. Who thinks it's one? Who thinks it's two? Seeing lots of ones? Good. Yes. So it is this bond right there that we are breaking. Okay. So if we are breaking this, the part over here that does not have that OME anymore, right? That doesn't have the leaving group anymore. That was our electrophile. And then the one that's attached by the alpha position, that was our nucleophile. Okay, then we do some counting. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That tells me that they are the same, which is good. Okay, so I'm going to draw that part first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and then I just need to add in what is here. So this X group, right, better match the ester and the base. So that X group becomes OME. Okay? So that, I think, is the best way to approach going backwards, figuring out which bond was being made, and then kind of go backwards. Okay, one last kind of practice problem here. Okay, first question. Does our base match our ester? Yes. Good. Okay, next question. Are we going to have a driving force? Like that? No, we're not. Right? We have one alpha proton. We do not have two alpha protons. We have one. Okay, so that means that this is going to be no reaction. We don't have two protons, we won't have that second deprotonation. Therefore, we're not going to be able to do the reaction. Okay, so you got to check these things every time, right? Every time. That's what makes it a little bit more complicated. All right. Any questions about the classic Claisen condensation before we just do all the variants on it? Okay. Yeah. Yeah, good question. So does temperature play a role in this reaction? Not in the same way that it does for the aldol. Sometimes you'll need heat for these just to get that leaving group to leave, but like it's not that big of a deal, to be honest. Yeah, you don't need to specify like, oh, I have to heat it a lot. Yeah, so it's not the same because we don't have the possibility of two different products, right? With the aldol, we had the aldol addition and the aldol condensation. Here we don't have that, right? Because we don't have an OH, so we don't have a way to dehydrate at the end. Good question. All right, let's do some variants on this. So again, this is the reaction. We're just now doing different versions of this reaction. So again, if you want to do it intramolecular, you can do it if you can make 5 or 6 membered rings. For some reason, the intramolecular version has a different name. So if you see the Dieckmann cyclization, that just means that it's an intramolecular Claisen condensation. I don't know why it has a different name, but it does. So that's the intramolecular variant. So let's give an example. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. So I'm going to arbitrarily decide that my right one is my electrophile. So this guy is going to be my leaving group. The red OET is going to be my leaving group. And then my left ester is going to be my nucleophile. It has 2 alpha protons, so that's good. And then if I number my carbons, 1, 2, 3, 4, 5, 6. If I connect carbon 2 to carbon 6, I will make a 5-membered ring. So again, we need 5 or 6 membered rings, so that's good. So if I were to do this intramolecular Claisen condensation, I'm going to make a 5-membered ring. We're going to number our carbons. So again, 2 and 6 are the ones that are bound. So we just made this bond right here. And then carbon 2 is still connected to carbon 1, which is this. I guess I can keep that color coded. Okay. And then carbon 6 should still have our electrophile carbonyl on it. That's carbon 1. Okay. So my challenge to you is to draw this mechanism. Take it step by step. Number your carbons. It's not actually different. It's not actually different. It just looks weird. All right. So draw the ring, number your carbons, fill it in. Okay. So I will post the answer to that challenge with the notes. So if you would like to go back and check, you may do that. But it's not different. It's the same reaction. Okay. And this is, again, symmetrical. So it's essentially equivalent esters reacting with itself. Okay, that's intramolecular. So let's talk about the crossed or the mixed Claisen. So similar to the mixed aldol, right? It is 2 different reaction partners. So the mixed Claisen so 2 different esters. And so in general, to get this to go and get one major product, you want one partner to not have alpha protons. So only one of the partners can form the enolate. So aromatic esters are common for this because that alpha carbon has no alpha protons. So that means that it must be the electrophile. And this must be our leaving group. And then you can mix it with an ester that does have alpha protons, like this. So here we have our 2 alpha protons. So we are going to have a driving force. Base that matches our ester. Acid. It's the same reaction, except the 2 R groups are different. That's the only change. So now we have our phenyl group on the left and our nucleophile ester on the right. So once again, we form a beta-keto ester. It's the same type of product. It's just that this R group and this R group are not the same. But the mechanism is the same, right? It's the same reaction. It's just only one of them can form the nucleophile. So that one's the nucleophile. There are very few choices to make. Okay, the other common one, if it's not aromatic esters, is going to be if it's just a hydrogen here. So again, if you don't have an alpha carbon, you don't have an alpha proton. So no alpha carbon, so no alpha protons. Right? If it's just a hydrogen there, there's no alpha carbon. Then you can mix it with something that has alpha protons. This. So again, we want to double check that it has 2 alpha protons. Yes, it does. Use a base that matches your ester. So OET in this case. Second workup step. That works. And once again, the product is the same, except our R groups are different. Right, so we've got one R group on the nucleophile. And now in this case, it's technically an aldehyde, not a ketone, that's in the beta position, just because that substituent is hydrogen instead of the alkyl group or an aryl group. Okay, so those are a bunch of different versions of the same reaction, but it's the same reaction. All right, 2 esters reacting with each other. Could be the same ester, could be different esters. Form these beta-keto esters. Okay, the last one we're going to go through is technically a different reaction because it's not 2 esters reacting with each other, but again, it's very similar. So this is our other learning objective, 21H. So this is the 4 Ps for the formation of beta-diketones from esters and enolizable ketones. Still in 21.4. Okay, so it is essentially a mixed Claisen, except the one that can form the nucleophile is a ketone instead of an ester. So our ester is going to be our electrophile in these cases, and you generally want it to be something that cannot form an enolate. So again, we have no alpha protons. And then an enolizable ketone. So it needs to be a ketone that does have alpha protons. So here we have 3. So 3 alpha protons. So we have at least 2. So good, that's good. Okay, so we can do essentially the same reaction. So first step, we're going to use a base. We're going to match our base to our ester. That's OET in this case. And just like in the Claisen, we're going to form an enolate, except this time we're forming an enolate from a ketone instead of from an ester. So I will abbreviate my phenyl like so, because it's faster to draw. And I generated an enolate. Okay, so I generated my nucleophile from a ketone. Now I'm ready to do my addition step. Nucleophile attacks electrophile, break the weakest bond. So again, enolates attack by pushing down a lone pair. CC double bond attacks our electrophilic site, break the weakest bond. So once again, we should be forming a tetrahedral intermediate. So we still have our sodium counter ion. Okay, we're ready to do our elimination step because we're under basic conditions. Collapse of the tetrahedral intermediate, leaving group leaves, just like nucleophilic acyl substitution. This is elimination. Like so. Once again, we still have alpha protons here, and they are more acidic than what we started with. So once again, our driving force is going to be the deprotonation of that at the end of the reaction. So we still have our base that we regenerated. That's going to grab one of these protons. And then once again, we need a second workup step where we add in acid so that we can reprotonate at the end. So the enolate pushes down, grabs a proton to get back to our product, which we had already made, but it wasn't going to stick around under those strongly basic conditions. And so this is our beta-diketone. Because again, in relation to one of the ketones, the other ketone is in the beta position. So that's why it's called a beta-diketone. Okay, hopefully that looks very similar. It's very, very similar. It's just a ketone instead of an ester as your nucleophile. Okay. Let's see if we can determine now what are our two starting materials if given a structure. So going backwards. Okay. So in this case, we need to think about, again, which bond is the one that's breaking. Could be this one, it could be this one. If we were to break that one, both of our partners would have alpha protons, which is not what we want. So we need to break the one where we will only have one of our partners have alpha protons. And so that would be this one. So again, it's like nucleophilic acyl substitution. So the part right here, where the acyl is next to the bond that we made, is the electrophile part. Okay. Come back to this X group in a second. And then the one that's attached from the alpha position is the nucleophile part. So, okay. And then what is that X? Well, it better match the base. I'm just going to make that into the ester that matches the base. Okay. So these ones are a little bit trickier when going backwards because you're not just having one starting material, you have two. So you need to be able to differentiate which one was the electrophile and which one was the nucleophile. It's a little bit less obvious, I would say, compared to the mixed Claisen. Okay, similar to the Claisen, right? We can also do intramolecular. So an example of that would be this. 2, 3, 4, 5, 6. So I could deprotonate one of these and then form a ring between 2 and 6, which would be a 5-membered ring. So if we were to do that under the same conditions, oops. So this is just to show you that like you have a lot of tools in the toolbox now to do lots of variants on the same reaction. Okay, so then I numbered my carbons. The 6th carbon is the one that turns into just the carbonyl. And then I should still have a carbonyl in the 3 position, like so. And so this bond between 2 and 6 is the one that I made. So again, I recommend kind of walking through it step by step by step, making sure that we understand how to do it intermolecularly and intramolecularly. It's not different. It's not different. They are the same. So in the last couple minutes, I just want to kind of put these 2 reactions side by side so that we can compare to the Claisen and just see how they're very similar. Right, so for the Claisen condensation, we have the beta-keto ester, and for this enolizable ketone and ester, we have a beta-diketone. So we have kind of 2 variants here. Okay, so the top one is our beta-diketone. The bottom one is our beta-keto ester. So the bottom one is the Claisen, the top one is kind of the variant on it. In both cases, we are breaking this bond. We have our acyl group, right? The only thing that's different is what is this group on our nucleophile. So in both of these cases, our electrophile part is an ester. And the same ester in this case, right? So ester and ester. The only thing that's different is the nucleophile. So in the top one, it's a ketone, and in the bottom one, it's also an ester. Okay, so they are essentially identical reactions. It's just like, where did your enolate come from? That's the only thing that changed. And so the bottom one is called mixed Claisen condensation, and the top one is not, even though they are the same reaction. Okay. All right, that's all I have for you today. Thank you very much. We will do enolate alkylation on Friday.